Let's start with a simple but powerful idea. Every SEC chromatogram tells a story, but only if we know how to read it correctly. When analysts talk about size exclusion chromatography, we often jump straight to molecular weight numbers, calibration curves, and reports. But behind every molecular weight value lies a quiet hero, the SEC calibration curve, and at the heart of that curve sit two deceptively simple concepts, CAV and void volume. In this session, we're going to demystify these concepts, not just theoretically, but practically, so that the next time you look at an SEC chromatogram, you'll understand why molecules elute where they do, what CAV is truly telling you, and how small calibration mistakes can create big analytical problems. At its core, size exclusion chromatography, or SEC, is beautifully simple. Unlike reversed phase or ion exchange chromatography, SEC doesn't separate molecules based on chemistry. There's no binding, no interaction, no attraction or repulsion. Instead, SEC separates molecules purely based on hydrodynamic size. Imagine a column packed with tiny porous beads. As molecules flow through the column, larger molecules can't enter most of the pores, so they take a shorter path and elute first. Smaller molecules explore more pores, travel a longer path, and elute later. That's it. No chemical interaction, just size and space. This is why SEC is so powerful for proteins and polymers. It preserves native structure and allows us to study aggregation, degradation, and molecular weight distribution without altering the molecule itself. The SEC calibration curve is where raw chromatographic data turns into meaningful molecular insight. This curve plots CAV on one axis and the logarithm of molecular weight on the other. So what exactly is CAV? CAV is the partition coefficient. It describes how much of the column's pore volume a molecule can access. A CAV of 0 means complete exclusion. The molecule is too large to enter any pores. A CAV of 1 means full inclusion. The molecule accesses the entire pore volume. Every real analyte falls somewhere between these two extremes. The beauty of CAV is that it normalizes retention behavior. Instead of comparing raw elution volumes, which vary between columns, it allows results to be transferred, reproduced, and understood consistently. Without CAV, SEC results become column-specific and hard to compare. Now, let's talk about one of the most underestimated parameters in SEC, the void volume, or VO. Void volume represents the volume outside the pores of the stationary phase. Practically, this is where very large molecules elute, molecules so big that they never enter the pores at all. Why does this matter? Because VO is the starting reference point for every CAV calculation. If VO is wrong, every single CAV value downstream is wrong. In real lab scenarios, VO is often determined using high molecular weight dextrans, blue dextran, or excluded polymer standards. One practical insight from experience: if your VO marker shows tailing or multiple peaks, that's a red flag. It usually points to column damage, sample overloading, or detector issues. To truly understand CAV, we need to clearly separate three volumes: VO, the void volume; outside the pores, VE; the elution volume of your analyte, VT; the total column volume, including all pores. Think of VO and VT as the boundaries, and VE as your molecule's position within those boundaries. This relationship is what makes the CAV equation so powerful and so sensitive. The CAV equation looks simple. CAV equals V minus VO, divided by VT minus VO. But analytically, it's doing something profound. It converts retention behavior into a dimensionless number that reflects molecular accessibility to pore volume. This is why CAV always sits neatly between 0 and 1, and why it's ideal for calibration curves. In regulated environments, this consistency is not optional. It's essential for reproducibility, validation, and regulatory confidence. Let's talk consequences. In polymer science, a small calibration error can distort molecular weight distribution, polydispersity index, mechanical and thermal property predictions. In biopharma, the stakes are even higher. Poor calibration can hide protein aggregates, oligomer formation, stability issues that impact patient safety. Regulators don't just review chromatograms, they review calibration logic. A strong SEC method is one that can be explained, justified, and reproduced across labs. From real-world lab experience, these are the most common pitfalls. First, void volume misidentification. Using inappropriate standards or ignoring early elution peaks leads to skewed CAV values. Second, incorrect column selection. If your analyte size range doesn't match the pore size distribution, the calibration curve becomes meaningless. Third, detector limitations. A poorly calibrated UV or RI detector can miss low-level aggregates or distort peak shapes. And finally, sample preparation. Unfiltered samples, aggregation during handling, or inappropriate solvents can sabotage even the best calibration strategy. In polymer QC, SEC calibration curves are the backbone of quality control. They enable accurate determination of molecular weight distribution, polydispersity index, batch-to-batch consistency. For industries producing medical polymers, coatings, or high-performance materials, this data directly impacts product performance and regulatory acceptance. In biopharmaceuticals, SEC is a frontline stability tool. It separates monomers, dimers higher-order aggregates. This allows scientists to quantify aggregation, optimize formulations, and ensure therapeutic safety. From monoclonal antibodies to drug delivery polymers, SEC calibration ensures that what reaches the patient is both effective and safe. Here's where experience really matters. Choose columns based on hydrodynamic size, not molecular weight alone. Match detectors, UV, RI, or MALS, to your analytical goals. Filter samples, control temperature, and document everything. And most importantly, recalibrate regularly. Columns age, systems drift. Calibration is not a one-time activity. To wrap up, CAV is not just a number, it's the language SEC uses to describe molecular size. Void volume is not a footnote, it's the foundation of accurate calibration. Whether you're analyzing polymers or proteins, a robust SEC calibration strategy transforms chromatography into insight. As SEC continues to integrate with advanced detectors and hybrid techniques, the demand for standardized, well-understood calibration practices will only grow. And when done right, SEC doesn't just separate molecules, it builds confidence in your data. Thank you for joining this deep dive into the science behind the SEC calibration curve.